Right, so welcome to Math 150, Multivariable Calculus, Lecture 6. What I want to talk about today is a little bit about level sets, a little bit about limits, and then a little bit about differentiability. The only question people had sent me was on orbits of planets, building on what we said last time. And so I'm going to use that as an interesting way to talk about limits and again about trying to look at data the right way. All right, so what I'm going to do now is start off with a little bit about level sets. So let me stop this share. All right. So I am using some commands in Mathematica. We will have a class in the near future just showing how to use it. I really don't care what system you use, but in the 21st century, you need to know how to use some system. If it wasn't so far and it wasn't so heavy, I would actually log in my huge table of integrals that I had when I was younger. I was told you had to have two, a portable one that you could have on you, and a big monster to keep at home. Completely different now in the 21st century. Now you can look things up, and the computers have wonderful symbolic packages to calculate integrals and derivatives for you. So you need to know how to use these tools. It also helps greatly to be able to see things. And so here what I'm doing is I'm doing a three-dimensional plot of a function. Actually, have two functions. The first function is just the function that's constant is h, and the second one is the sine of xy divided by xy. So this is a great limit problem. The sine of h over h as h goes to 0 is just 1. So this function is actually well defined. And if you look, the first thing you should always do is you should look at the axes. And the axes here are going from basically, maybe negative 0.1 to positive 0.1. So much, very far below 0, 0, which gets pushed all the way up to 1. So if you were to continue this higher, it would be spiking. I want to be able to see some of the behavior. When you have a function that varies wildly, you sometimes worry about how well is the program graphing. Could there be some issues? Now the other function is just h. How does that depend on x and y? It doesn't. So what is the plot of h going to look like? If it doesn't depend on x and y, what shape will it be? So for every value of x and y, I go up to height z. I go up to height h. What surface will that look like? It's a plane. At what height above the xy plane? H. And so this is a great way to look at level sets. If I look at the intersection of this function and my plot sine of xy over xy, that will give me the level set of height h. And so Mathematica has a beautiful command called manipulate. And so I'm allowing c to range from 1 to 0.001. And I'm plotting x from negative 10c to 10c, y from negative 10c to 10c, so I can zoom in or out by changing c. And so if I come over here, if I play with this a little bit, I've zoomed in a lot. And now you can see I'm actually going all the way up to height about 1. I'm really seeing what's going on, and I'm seeing how it's curving down. You can see a lot of the symmetries of this function. The x movement should be the same as the y movement if I flip the roles of x and y. But it is going to depend on the angle from the origin. This is not a function of just x squared plus y squared. And now the second one, h, if I press the plus sign here, I'm showing you the value of h is 0.03. Here the value of h is negative 1.45. And not surprisingly, it doesn't intersect the surface at all. It's too far below. If I go too far high, it's going to be above. What do you think the first point is where it's going to intersect sine of xy over xy? Yeah, so we can move things all the way down to 1. And here is just a little bit above 1. And now if we move it down to maybe just a little bit below 1, you can see, oops, somehow it just doubled. And you can see now It's just a little bit below, and we're beginning to get a little bit more of a region. If I go all the way up to 1, it should just give me just that point over there, which you're not going to really be able to see. And as I move it down further and further, down to 0.9, you can start to see more and more. I can slide this down, and you can see how the level set is moving. So this is a really nice way to physically see the level sets in action. I have my plane, and I'm moving it up and down. What if I had a function not of x and y, but x, y, and z? I would have to do a 4-dimensional plot. Not going to happen. So for the most part, when we're trying to physically see things, functions of 2 variables, and the third variable is the height of your function, that we can do. Beyond that, not really. And then you can just change the function you want here. And so the code is very nice. And this allows you to zoom in and out. This allows you to move your plane up and down. Any questions about this? Okay, so the next one that I wanted to show So what I want to do here is I want to talk a little bit about plots of planets. And so in an ideal world, and this idea goes back to the Greeks, circular motion is just awesome. And wouldn't it be wonderful if everything moved in a circle? And what should the circle be centered on? At least if you go back to a lot of the ancient Greeks. Maybe not all, but a lot. What should the heavens be revolving around? The Earth. Some said the sun, but you have some point. And so here I'm plotting the function cosine t sine t. Now, let's start with an easy one. So here I'm just plotting cosine t sine t. T goes from 0 to 2 pi c, so I can go around a couple of times. And I can hit play, and we can watch the planet moving in perfect circular motion. I'm just going to keep tracing that up. And so for millennia, people believed all motion was circles. And so here is the simplest example of a circular motion. You could make this more complicated. Now here's a nice twist. What I'm going to do is cosine t sine t, and then the z-coordinate is t over 20. What kind of coordinate system does this look like? Okay, cosine t, sine t, and then t over 20. Looks like cylindrical. So as time passes, if I ignored the t over 20, I would just keep going in a circle in the plane. But what's going to happen because of that t over 20? What's going to happen as time passes? Is it going to keep going in that xy plane? What kind of shape is it going to look? If it wasn't for that, it would just keep going in a circle. But because I have t over 20, what happens to that circle as time passes? I'm sorry? It looks like it's... Well, a cone would be getting narrower. So do you think it's going to get narrower, or do you think it's always going to stay the same size? Yeah, the x and the y coordinates are just cosine t sine t. Let's just keep going in a circle. What happens to the z coordinate as time passes? It's going to increase. So instead of just being a circle in the xy plane, what do you think happens to that circle? It's going to spiral up. And so if you look what happens, you can see it spiraling up. And what's nice is you can actually slow things down if you want. And you can see as time passes, if you were to look straight down on it, you would still see that circle motion. But we now have that vertical height, that c. Okay. The next one starts to get more interesting. And so now, all right, so this is just circle motion. Right, that's not a big deal. And what happens if I change this one? This one. Okay, things are beginning to happen. beginning. So what is going on here? So I have cosine t sine t, and I'm going to just plot that. So this part over here, this is the first function I'm plotting. So what is that? So that's a circle. So the blue one is I'm just going to always plot a circle. So as t goes from 0 to 2 pi c, that tells me how many cycles I do. This first thing is always going to plot a circle. The second one is cosine t plus r cosine ts, sine t plus r sine ts. If r equals 0, it's the same circle as before. So over here, the last one is r. So if I make r 0, the two circles align. What does s do? Well, this is plotting a circle on a circle. If s equals 1, it's going to be going at the same speed as this one over here. But as I change s away from 1, so if I put s at 0, then there's no motion at all. And I'm just going to have some shifting. But now, if I increase s a little bit, I can start to get some interesting shapes. Did any of you ever have those, spiral things, the little circles with teeth, spirographs or something like that? And you could have the teeth inside other teeth and make curves like this. And so you can start getting some very interesting shapes. A lot of it is going to depend on whether or not you have purely rational angles. And you could just see that it was beginning to have some kind of little phasing. And the question is that because it's not perfectly aligning, or is it because of some rounding errors? And the last one coming down is, again, cosine t sine t. That's just my standard circle. That's the blue one over here. Then cosine t sine t, and I'm adding a little bit to it. And so I'm adding, again, a circle on that. And then by changing what s is, I can change the speed of that. And so, if I put s all the way down to here, and I've got some r over here, I could pause. And sometimes, it just needs a little bit of time to say, look, you're asking too much of me. Okay, don't trust the data that you're seeing. Give it a moment to pause, do the calculation, and look at things. Okay, that's a really nice curve. And I can say, well, what would happen if I keep changing r a little bit? And the smaller r gets, the closer it is to a circle. And then as I change s, I can change the frequencies of things. And then the question is, are there choices of s that might be interesting? What if s is your perfect integer? Here s is 4. I love how it says my internet connection is unstable. That looks like a very interesting shape. And so if I tried, maybe 6, another integer, again, getting a very nice curve. If I tried 6.0103, a little bit off, you can see that it's not quite coming on itself as quickly. It might take more iterations before it aligns. And so one of the ideas that people had classically was to try to approximate the complicated motion of planets by circles on circles on circles. So you travel in your main circle. And then on that main circle, you can have another circle turning and you're on that. And if that's not enough, what could you do? Another circle. So you could have your main circle, and then on that circle you have another circle that you're on, and you have one on that you're on. And what if that's not enough? You could have even more circles. So one of the goals of today is to talk about limits. That was one of the big things in the lectures that's going on. Most of the time, you've seen limits by looking at limits of functions, limits of sequences. I thought it might be interesting to do limits of shapes. And if I start adding more and more circles, the question is, what kind of shapes can I construct? And with enough circles on circles on circles, you can actually construct a very rich class of shapes. And the hope was that you could describe planetary motion just by using circles on circles on circles. What might you be a little bit concerned about with using circles on circles on circles? So do you like the idea of circles on circles on circles? And if it's not quick enough, just add more circles. What might be concerned about this? How many circles do you add? Is this a natural way to do things? Now, I know they keep changing the curriculum a little bit in terms of what you guys did in calculus versus what I did in calculus. You are not supposed to have seen, or you're not required to have seen Taylor series before coming here. How many of you have seen series expansions for functions like e to the x or cosine x? Where we have e to the x is 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial, and so on and so on and so on. And then cosine of x is 1 minus x squared over 2 factorial plus x squared over 4 factorial. And sine of x is x minus x cubed over 3 factorial plus x squared over 5 factorial. And it turns out e to the I x is cosine x plus I sine of x, where either I is or I am the square root of negative 1. So these are very famous sequences. And when we're trying to calculate limits, the idea is by taking more and more terms, the hope is that this will converge to something. So we will do a lot on this later in the semester. When we get to the final unit, when we do sequences and series and convergence, it turns out for any value of x, all of these series converge. And here, with n factorial is n minus 1, 3 times 2 times 1, 0 factorial is 1. It's the number of ways to arrange n objects in order matters. It turns out that this function is initially only defined for the integers, but you can extend it to other numbers, in fact, all complex numbers. So we want to talk about when do limits exist. So our goal at the end of this semester is to talk about stuff like this. If there's time later today, I might show you how to derive all of trigonometry from this formula right here. This is a highly non-trivial formula, incredibly powerful. So we only talk about limits. And frequently, I might have a function like this. Here's some function x naught. Here's the value L. And we'll say the limit as x approaches x naught of f of x equals L. And that means as we get closer and closer and closer to x naught, our function is getting closer and closer and closer to L. We could have our function defined to be something else at the point x naught. When we talk about x goes to x naught, x is getting arbitrarily close to x naught, but it's never actually equal to x naught. What kind of function would it be if it's getting closer and closer to L, jumps up instantaneously, and then jumps back down and continues? That would be a discontinuous function. And so a continuous function is continuous if f of x naught equals to 1. And so we often like to look at functions that are continuous, or even better, continuous and differential. So we have a whole slew of rules. And the limit of a sum is the sum of the limits. The limit of a product of the limits. The limit of a quotient of the limits. Except we have to be a little bit careful. As we talked about this earlier in this lesson, whenever you have an infinity involved, that is a danger. That means you've got to be careful with what you're doing. So if the limits are finite, we can do all this. The limit of a finite sum is the finite sum of the limits. As soon as one of the limits is infinity, then you've got to be very careful. We saw we can't really talk about infinity minus infinity. It matters how they are approaching. We saw we can't do infinity times 0. We gave an example in class of a perpendicular line, which I think was in the video from today, where that limit could naturally be defined to be -1. And so we want to calculate this. The key limit in calculus is f prime of x is the limit of h goes to 0, f of x plus h minus f of x over h. And if that limit exists, we say that that is the derivative of the function at the point x. It's a new function. I said if the limit exists, then we say the function is differentiable at x, and the derivative is f prime. Did that clear it up? Oh, interesting. Okay. I am using the live transcript now, and so I'm going to try to take the transcripts of all of these and send them afterwards. It could be saved. Launch photon torpedoes. I know Alexa can launch photon torpedoes. I think they use the next generation sound effects for that one. So this is a great notation in some regards. It's related to f. So my notation has the symbol f and has a prime in it. The problem is if we have functions of several variables, well, what derivative am I taking? What do I mean when I write f prime? And this is why when we have several variables, we write partial f, partial x. The point x naught, y naught. To be the limit as h goes to 0, f of x naught plus h y naught minus f of x naught y naught over h. This should remind you of the notation dx from before, when f is a function of one variable. So when we have multivariable calculus, this is far better notation. Because you can look at it and you can see what the derivative is. So there's the theoretical definition of what the derivative is. And then there's how would we compute them? Well, this basically looks like it has one problem. Just keep y constant. So if I give you f of xy equals 3x squared y to the 4th, and I want to calculate what is the partial derivative with respect to x, I should do this as take the derivative with respect to x of 3y to the 4th times x squared. And I'm writing this over here because this whole thing is a constant. I'm fixing y. If you want to imagine y equals pi or e or one of your favorite numbers. And so what would the derivative of x squared be with respect to x? It would just be 2x. So what's the derivative of c times x squared? If I give you c times x squared, the derivative with respect to x is just 2cx. So this derivative is just going to be 3y to the 4th times 2x, more commonly than the 6x and the 4. So an entire large chunk of the course is essentially this small little segment right here. If I give you a function of several variables and I want the partial derivatives, just hold all variables but one constant. What if I gave you f of xy is x to the 4th y squared plus y cubed, and I want to calculate df dx? What would that be? The derivative of the sum is the the sum of the derivatives. If I want to give you a difficult test, can I? Yes or no? Oh, absolutely, yes, right? It's not a challenge. Which do you think is harder for me, to come up with a hard function to take the derivative of, or a hard function to find the integral of? Which is harder, differentiation or integration? Integration. The big lie of Calc 2 is that you can integrate. You can't. If it makes you feel better, I can't integrate either. Nobody can integrate. We have a couple of functions that are really nice, and we have closed form expressions for their antiderivative. But most functions do not have nice integrals. If I ask you, what is the integral of e to the x squared, there's no nice closed form solution for that. What's the integral of cosine of x? So you could say it's sine of x and say, yeah, or if you want to put on a plus c, you say, aha, it has a nice antiderivative. Yes, but what are sine and cosine? If they're given by these infinite series, just because I give it a name doesn't necessarily mean I can calculate it easily. We can calculate sines and cosines very easily at certain nice angles, and then we can use the angle addition formulas to approximate things. But in general, it is a pain. Any fans of the comic strip Foxtrot? There's one strip when the young math geek Jason's helping one of his older siblings with math, and he's helping with some traits, and he's asked, what is the value of cosine of the following? And he starts rattling off the infinite series. And the sibling says, I'm not paying you by the hour, I'm paying you a flat rate. Oh, and it's just 1/2. Sometimes these things have incredible cancellations. When you look at this, when you put in pi over 3, the cosine of pi over 3 is 1/2. When you look at that, 1 minus pi over 3 squared over 2 factorial plus pi over 3 to the 4th over 4 factorial, that simplifies to 1/2. Looking at that infinite sum is not necessarily going to be that illuminating. We can approximate it very well. And in fact, factorial grows extremely rapidly. You don't need that many terms to do a good job. But to see that it becomes 1/2, that's not the reason. Over here, it's very difficult for me to stump you with a derivative because we have our rules of differentiation. And whatever I give you, you hammer away. If I give you a sum, what should you use? A sum. If I give you a product, you should use product. What if I give you the cosine of 3x squared minus 7? What should you use for that? Chain. Whenever you hear of, that is a big hint that almost surely the chain rule is going to make an example. The cosine of, oh, this is f of g of x. I can't give you a function that you can't differentiate. It may take you time, but I can't give you a function that you can't differentiate. I can easily give you a function you can't integrate. If you're ever asked to integrate something, how can you tell if it's right? I'm sorry? Yeah, take the derivative. So if you could ever check your work, try to do so. So here, we would take the derivative of both. So it would be the derivative with respect to x, of x to the 4th y squared, plus the derivative with respect to x of y cubed. So what's the derivative with respect to x of x to the 4th y squared? 4x cubed y squared. And now what's the derivative of y cubed with respect to x? Sorry? So what's the derivative of 5 with respect to y? I mean, 5 with respect to x? 0. What's the derivative of 17 with respect to x? 2021. 0. What's the derivative of y cubed with respect to x? 0. That has no x dependence. It's a constant. The whole way you take partial derivatives is you consider all the variables as constants, but the one over here. Now, if you look at this, when we take partial derivatives, we are putting in a coordinate system in the problem. Now, that's not too surprising. If I have a function, I should have some way to talk about the variables, to talk about the input. But we have now put in preferred axes. When we take df dx, we are approaching along the x-axis. When we take df dy, where are we approaching? Along the y-axis. And you remember, we talked about scribbles, or those strange paths. And so when we talk about df dx and df dy existing, they might exist along those paths, but maybe they don't exist along arbitrary paths. And so a big part of the subject is when is it enough for the derivatives, the partial derivatives to exist, and what properties do they need to imply that the function is differentiable? So you have to figure out a way to generalize the notion of what it means to be differentiable. So we have f prime of x is the limit of h goes to 0, f of x of h minus f of x over h. Let's do it at the point x naught. Another way of writing this is it's the limit as x goes to x naught of f of x minus f of x naught over x minus x naught. Do we agree that that's another way of writing the limit? How would you relate this to that? X equals x naught plus h. And so as little h goes to 0, that's the same as x going to x naught. Another way of looking at things is the limit of x goes to x naught of f of x minus f of x naught minus f prime of x naught x minus x naught over x minus x naught equals 0. This is another way of saying f prime of x naught is the derivative of f at x naught. What I've done is I've moved the f prime of x naught over to the side. Does this have any x dependence? As I vary x, as I send x to x naught, does f prime of x naught change? Or is it constant? It's constant. There's no x dependence. X naught is a fixed number. Think of x naught as 5, 17, 2006. Well, if it's constant, I can bring it inside the limit. And then I can multiply by 1, by x minus x naught over x minus x naught. And so when you do the algebra, I want you to just do it slowly. This part over here is going to cancel. It's going to give you the minus f prime of x naught. I'm just combining two fractions. And so another way to say that a function is differentiable is to say if I subtract this quantity over here, it's so good that as x goes to x naught, not only does the numerator go to 0, but it still goes to 0 when you divide by x minus x naught. If my function is continuous, if I don't have the x minus x naught in the denominator, as x goes to x naught, what does x minus x naught go to? What does x minus x naught go to as x goes to x naught? It goes to 0. So as x goes to x naught, this piece is going to go to 0. If my function is continuous, f of x is going to go to f of x naught. So the numerator goes to 0 as x goes to x naught. It's not a big deal for the numerator to be getting smaller and smaller and smaller. But what we're seeing is, it is such a good approximation that even when you divide by this very small bit, it still goes to 0. Ah, now we have something. And what we're really doing is one of the big ideas in calculus. If I have a function, what we're trying to do is we're trying to approximate an arbitrary function with its tangent line at a point. We're doing the best fit line. And what we're doing is we're using the coordinates of this point, x naught, f of x naught, and then the slope is x prime of x naught. That's our instantaneous speed. Should your instantaneous speed change a lot in a small amount of time? So if you're traveling 60 miles a second, which is a little bit faster than most of us, if they have experience, but let's say you're traveling at 60 miles a second. How far have you gone in 1 second? 60 miles. How far have you gone in 1/60th of a second? 1 mile. And so if your speed is not changing that much, what this is saying is, look, I can approximate where I am by where I stopped, plus my instantaneous speed at the key time times the elapsed time. And this is y minus y naught of x naught equals the slope x prime of x naught times x minus x naught. That's the equation for tangent line. And we can rewrite that as y is f of x naught plus f prime x naught x minus x naught. And what this is saying is that the tangent line is a really good approximation to the function. That f of x minus the approximation is going to be really small. If you think about it, if you move a very small amount of time, there shouldn't be that much of a difference. And so if I just want the numerator to be small, it's not a big deal. But having this whole quotient be 0, that's significant. This is what's going to generalize. And instead of subtracting off f prime of x naught, we're going to subtract off not the tangent line approximation, but the tangent plane. And if we went even higher dimensions, we would subtract off the tangent hyperplane. That's how it's going to generalize. So again, there's many different ways of writing. So let's consider f of xy equals xy divided by x squared plus y. And I want to calculate the limit as xy goes to 0, 0 of f of xy. Why do you think 0, 0 might be an interesting place to look at? It is undefined. What happens to the denominator at 0, 0? It's 0. But the numerator is also 0. And so you have a chance of something happening. So we want to try to figure out, does the limit exist? So the simplest thing we can do is try some path. Can somebody give me a path to get to 0, 0? Thank you for being kind. Yes. Let's come along the x-axis. Right? If we come along the x-axis, y equals 0. Right? So along the x-axis is the limit as x goes to 0 of x times 0 over x squared plus y squared. Well, what is this expression parentheses equal? Oh, so y is equal to 0. What is this equal? It's the limit as x goes to 0 of y. not 1 over x. What's the numerator? What's the denominator? And x is not equal to 0. If 0 divided by x squared, x gets arbitrarily close to 0, but x is never 0. So what's 0 divided by x squared? 0. So what is this number equal? 0. By symmetry, where did you get it along the y-axis? 0. The easiest way to see that is I can't tell the difference between x and y. If I flip them, I have the same function. So whatever's happening along the x-axis, I should be seeing the same thing along the y-axis. So does this mean that the limit is 0? Okay, why not? I kept 2 paths. You can come in different directions. Does anybody know the longest song to sing? Infinitely many bottles of beer on the wall, infinitely many bottles of beer. Now what do? If you're over 21, take one down, pass it around. And now, we started with infinitely many bottles of beer. We took down one. How many bottles are left? Infinitely many bottles of beer on the wall. The song will never end. If you don't move this song. We checked 2 paths. There are infinitely many more to go. Are we making good progress? But all we need to do is find 2 paths that give a different answer. And if we find 2 paths that give a different answer, can the limit exist? No. If every path we checked is the same answer, we start to gain confidence that the limit exists, or that we are just not that creative in choosing paths. What would be a good path to try next? We tried x-axis, we tried y-axis. What would you try next? Diagonal. So we could try along x equals 1. Or more generally, you could try along maybe y equals mx. And that way, by introducing that 3-parameter m, we're trying all these lines at the same time. And now we would get the limit as x goes to 0. If y equals mx, we would have mx squared over x squared plus m squared x squared. That's the limit as x goes to 0. What do we get? What does the numerator and denominator both have in common? They both have an x squared, so we can cancel the x squared, and this is going to be m over 1 plus m squared. This is a particularly nice limit to do. Is there any x dependence? For every value of x, I give you m divided by 1 plus m squared. So what is the limit of x goes to 0? Every value of x, I give you m over 1 plus m squared. So what will the limit be? It would just be m over 1 plus m squared. So we've just shown that if you approach along the line, you get a different answer depending on the slope of the line. And if we know the special cases of the vertical and horizontal, so who knows who Pavlov was? Yes. What is Pavlov famous for? Classical conditioning, right? So there's a couple of classical conditionings that I want to do on you. And so I don't get into trouble, I'm mentioning that I'm doing this a little bit. One of them is whenever you see a product, you should be thinking of a logarithm. You've got xy over x squared plus y squared. Does any of that remind you of something you might have seen before? That might be a good change to do. You've got an x squared plus y squared. Yeah, so what should we do? We should convert to instead of looking at Cartesian and xy, what should we do? Use polar. So x is our cosine theta, y is our sine theta, x squared plus y squared is r squared. And so the limit of xy goes to 0, 0 of xy over x squared plus y squared is the same as the limit xy is going to become r squared cosine theta sine theta divided by r squared. Now, if xy goes to 0, 0, what happens to r? So if xy is going to 0, 0, what happens to r? Inside? It goes to 0. And what about theta? Do I have any restrictions on theta, or is theta free? So if r goes to 0, will it still go to 0 no matter what theta does? Yeah, this is just giving you a point, r units from the origin. Theta is free to do whatever the hell it wants. And that's how you get all those strange paths. So if we can just study the limit as r goes to 0, then it can do whatever it wants. Oh, well, the r squared canceled, and this is just the limit as r goes to 0 of cosine theta sine theta. And now, the limit will depend on what theta does. If theta is constant, then you'll just get cosine theta sine theta. If theta itself is spinning, then the limit won't exist. But this is enough to see that the limit will not exist. So if fixed theta can get different values. And there's one last limit I want to do. Limit as x goes to infinity of, say, 3x to the 4th plus 7x cubed minus 2x plus 1 over 4x to the 4th minus 3x cubed plus 2. So when I look at something like this, as x becomes very, very large, what does the numerator look like? If x becomes huge, what does the numerator look like? It looks like what? Yes, to be specific, how does it grow with x? It looks like approximately. It looks like approximately 3x to the 4th. If that's in a quadrillion, this is going to be a quadrillion to the 4th. This is a quadrillion cubed. The 3x to the 4th is going to kick the 7x cubed, which trends. And same thing for the lowest. So what I can do is I can pull out the highest power of x from the numerator and the denominator. So I can get 3x to the 4th, and it'll be 1 plus 7 over 3x minus 2 over 3x squared plus 1 over 3x cubed. And for the denominator, I pull out a 4x to the 4th, and I'll have 1 minus 8 over 4x plus 2 over x to the 4th. So as x gets very, very large, let's see what happens. You agree I can cancel the x to the fourth. So these would cancel. And then as x becomes very, very large, what does this fraction look like? Well, this looks like 1 up here. And this looks like 1 over here. As x gets large, all this becomes insignificant. So this would just become 3/4. And so this is how you would take the limit when you have, a ratio of 2 polynomials. If they have the same degree of their leading term, you're going to get some nice constants. If the numerator is larger than the denominator, it goes to infinity. If the denominator is larger degree, then the numerator goes to infinity. All right, I think this is a good place to stop. Any questions? Yes. Yes, so if you fix theta, you get cosine theta, sine theta. But different choices of theta will give a different limit. So if you fix theta to be 0, you always get 0. If you fix theta to be pi over 4, you'll get root 2 over 2, root 2 over 2, so you'll get 1/2. So you actually get different limits for different fixed values of theta. If you allow theta to vary, you could take theta to be 1 over r, so it's cycling over. Or take theta to be r and getting smaller. And if you do that, you can get strange things to happen. And so this is a function that it has limits along the x-axis, along the y-axis. It even has limits along straight lines. But those limits are not all the same. Imagine though it has the same limit along straight lines at any angle. What would you try next? So if you got the same limit along every line, what would you try next? What's the next simplest thing to try? Next, check out the line. The line is y equals x. What would you try next? I'm sorry? The plane? No, well, we're still in one, we just have one variable. Y equals x with a line. What curve would you try after y equals x? What curve? Y equals x squared, you would try a parabola. It's possible to come up with something that's the same along all the lines, but different along parabolas. If I really want it to be cruel, I could have something that's the same along all straight lines, all parabolas, but not on cubes. And so just because you check it a couple of times does not mean it's always going to work. Okay. So what I want to do now, I'm going to save the transcript. Okay. I will stop.